All right, guys, let's slowly get started. I have tutoring. I offer tutoring for 3 days. So if this time doesn't work for you and you want to try outside of this range, let me know, and I'll see if I can make that. But we got Friday. That's in this room, right sort of next door. It's down the hall. 12, so noon to 2. And then Monday, Tuesday next week, noon to 2, and it'll be in your lab room, so McLean 174. There shouldn't be any labs next week, so the room is free for us to have some tutoring. Just let me know if you can make it, or if you'd like to go, but maybe the time doesn't work. All right. Why don't I get started? I want to try this one. This little, it's called a Heroes engine. I looked it up. And hopefully this one is better. I might have too little water in it, but we'll see. Let's see. There you go. Something. Also, you have to realize it's not sort of hanging in the middle of the string. Back off a little bit. Let it unwind. And I had a backup just in case. But that's the theory. As this gas is expanding, it's able to push stuff out of the way. In this case, it's just the gas shooting out of these little vents that's able to make this thing spin so violently. I'll try to get it up there.
And what's causing it to spin?
What's causing it to spin? There is steam shooting out of some small holes that I have in the side of the can. So if you want to come up a little bit afterwards, take a look. There's another one that has some visible holes in the can. I have 2 on each side. And they're sort of angled at one's angling that way, one's angling this way. So when the steam comes out, it's able to push it in a circle. I'll just do this one afterwards, just for fun, after class. Okay, so we were talking about engines. We're talking about things that, as they expand, they're able to do work. We talked about first law of thermodynamics. Let's talk about the second law of thermodynamics. So this is sort of a 2-part law. The first part sort of includes engines. So it's basically a general statement that says no engine can be 100% efficient. So that's some sort of like more technical phrasing up top, and I've paraphrased it underneath for you. So the energy that's, if we remember what we were talking about heat engines last time, there's this hot reservoir. It has to go through some sort of system that's able to push out some work, and then all of the excess goes into a cold reservoir. So what this is saying is that no engine can sort of fully utilize all of the energy in that hot reservoir. So should have brought out the sort of car piston example. So no car engine, no heat engine of any kind can take all of the energy from that little gasoline explosion inside of the piston. Your body can't absorb 100% of the food energy. There is no way for due to the second law of thermodynamics, there's no way for a heat engine to absorb all of the energy from that hot reservoir and use it to perform work. The second half, or the second part, is sort of a two-part law. States that energy will always flow from a hot system to a cold system. This sort of feels a bit like they're sharing the limelight. So when you leave the fridge door open, you're not letting the cold out, you're letting the heat in to the fridge. If it's a cold day, you are letting the hot air out of your house when you leave the door open. All right. Let's see, what else do I want to do today? That, and that. Yeah, okay. All right. So, talking about engines and talking about things that are, gases that are expanding, and then maybe they can contract again. Maybe I add some heat to a gas, I add some energy to a gas, and it expands. Well, if I slowly and steadily wait for the energy to come back, the gas will return back to its original state. This is what's called a reversible process. It's somewhat finicky in that energy doesn't behave like that. Energy is a little tricky to keep contained. So if we have something that is reversible, you move all of these. If we have something that's reversible, we should expect if we do an action, we put energy in, and we do the exact opposite, then it will return to its original state. So my example I have for you is a piece of paper right here. I will take this paper and with my two hands put some work onto the paper and crumple it up. Okay? All right. And now I have a ball of paper. So if this was a reversible process, the paper would do work on my hands and it would uncrumble itself perfectly flat again. And then I put it back down on the table. Imagine me crumbling, but I reversed the video. That is a reversible process. Well, I can still uncrumple this. This is what's called almost reversible. Things aren't always as clean and simple. Same idea with energy. If I add energy in, it's still kind of a little messed up if I want to see if I get that energy back. Same with this. I uncrumpled it, but I had to add more work in, my own hands, uncrumpling it. Probably the same amount of energy it took to crumple it into a ball. Similar, a more extreme example is a car crash, something like that. same exact thing of me crumpling this up. I'm putting energy in to change this thing somehow. If this was reversible, I say perfectly reversible, the wall would put all the pieces back together, the car, and then push it backwards. That's not how things happen in nature. So, yes, you can fix a car after a crash. You can uncrumple a piece of paper. It's almost reversible. All right. So, that's just the way nature likes to do it. So, what else is maybe just kind of reversible? Maybe just a little bit. Maybe even if it's like a little messed up. Well, what if I have something that is, maybe this is a note and I'm going to get rid of it. I could crumple it up, but that's somewhat of a reversible process. Someone can take it and uncrumple it. What if I explode the thing or rip it up? Rip it up into pieces and then throw it in the trash. Is this a reversible process? So, yeah, I can take the pieces, put them back exactly the way they were. Somewhat looks like the way it was before, even though it's not quite the same. Same thing, imagine this going on with energy. Energy has a way of sort of leaking out and bleeding out into space somewhere and not turning out the way you expected it to be. So, like that watermelon, you can find all of the pieces, you can find all of the watermelon juice, collect it up, put it back together, and it will kind of look like a watermelon, probably not. But it will be semi-reversible. All right? Same thing with this. If you have a note on there, someone can figure out what the note is. What is an irreversible process? That's when the odds of putting something back together, like this piece of paper, okay, you say, someone can put that back together. I've shredded my tax documents, but someone can still put in that amount of energy. I could go smaller, 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 but I'm still able to, if I was willing to put the energy in, come back to the original state. I should have put up some pictures of people they found have gone through shredded papers and just like hundreds of shredded papers, full documents, and they've meticulously lined them up and taped them all together, and they have your information. So if you want a secure way to shred stuff, typically, big business firms and stuff like that, they do like 2 or 3 times shredding. So they take it, shred it once, take those shredded bits, shred it again, maybe one more time. That way the paper, it's not worth it anymore. It's not worth the effort. What's irreversible? In this case, if I have a note I don't want anyone to get to, and I make the odds so far against reversing this thing, I need to do something that uses a lot of energy really quickly. So I can do this. Now what's happening to the paper? It's burning.
It's turning into a gas.
Turning into a gas. And it's all still there, but it's turning into trash. Yeah, like that.
It's ash.
Ash, yeah, it's also trash. So we have this still here. All the information is still here. All of the little ash particles, they're scattered in the air. If I want to reverse this, It's so astronomically impossible for me, I can call it irreversible. And, you know, if I had some sort of magic machine that was able to do this for me, what would it have to do? It'd have to find all of these scraps. It would have to take all of the energy of the heat from the fire back out of the room. This room is a little bit warmer now since I did that. It would also have to take the light it sent out to you guys as you saw it. That was energy. So it has to take all of those things back and recombine it in order to get that note, that piece of paper again. So since that's so wildly impossible, or I should say improbable, that is what I can call irreversible. That's an irreversible process. So similar, this is what everyone's going to do at the end of the semester with their notes. Burning something, that is actually like physically changing its chemical structure. That's something that I don't have the time to do as a human being to redo and put back together. So that's a thing of like a gas expanding. If I wait long enough and I wait steadily, the gas will return back to its original state. And that's really, really close to being a reversible process. Why am I talking about this? So I said earlier, we were doing engines, that in the second law of thermodynamics says there can be no 100% efficient engine. And that's because of this sort of energy's always going everywhere. There's always energy finding its way to leak out of the system. If there was a perfect engine, it would be called the Carnot engine. The Carnot engine is just a big sort of thought experiment. It's not physically possible to make one. So, once again, the second law says that you cannot have a 100% efficient engine, heat engine. So, what's the closest we can get? That is a Carnot engine. So, this is, factoring in like energy is going to bleed out somewhere. It can only absorb so much energy from that hot reservoir. This Carnot engine, it has to use a reversible process. Let me do a little picture on the board. I'll put one on the screen later. This was the hot reservoir. Cold reservoir. So in order for that steam engine, in order for your car, in order for you to physically do work, a force over a distance, you have to take some sort of energy from a hot reservoir, and it sort of goes through some sort of process. It's either your, if it's your own biology, that's like your stomach taking your food and running it through your muscles. You're able to produce work. And then there is, whatever the excess is, it goes into a cold reservoir. For your car, it takes the gasoline, it gets really hot, hundreds, maybe thousands of degrees in the engine as it's is taking the gas and exploding it inside of the cylinders. That's the hot reservoir. And it goes through, turns all of the gears. And the cold reservoir for your car, that's the air that's coming out of your exhaust pipe right here. So, the Carnot engine, it has to use this reversible process. And because it's using a reversible process, in order to keep it running, so instead of going from hot to some sort of system and then down to cold, it then has to reverse this thing. It has to go up, it has to go up, and then there has to be work put in, that's minus work. And then it goes back up to the hot system. This is perfectly reversible, which I said at the beginning was kind of not realistic. Energy bleeds out places. Energy dissipates. So it takes the energy, it produces some work, but then that work is needed to go back into the system to have the system cycle around. This is one cycle of this engine. You see, it's not very productive. If you add these two together, it's not producing any work. This is a useless engine. It's not going to do anything for you. This is something that reminds us of a, if you've ever heard of a perpetual motion machine, something like this, or that. People will try to sell you something that says, this is free power, this thing will go forever. You can hook it up to your you can hook up to your power system and just give it a push and it'll go forever. Say goodbye to the electric bill. The thing is, these work for maybe a little bit, but the second law of thermodynamics says that energy is being lost somewhere. Somewhere in that one also. This one, I think there's a pump that's hidden, that's actually pushing the water back up. But these may work for a minute or two before friction gets to them and before the energy fades away. It's not that energy is being destroyed, it's just going other places. If you're able to hear it, that means energy is traveling through the air and going all the way to your ears. So that's energy being lost in some manner. All right. Let's see. What else is next? We have entropy. All right, and this leads us to the discovery of entropy. Us saying like, well, it doesn't appear that any engine can take in all of the energy. And where's the energy go? And why is this sort of a thing that naturally happens? We can call this entropy. Why is the universe prefer to have things disordered? So if let's see, how do I want to do this? If I have a couple dice and I have them all arranged the same way, I'll have them with 1 on the top. If the universe prefers order, it will keep things all nice and neat in the same category. Everything will be nice and separated. And it's the easiest thing to prove with just general dice like this. I could drop them. The universe doesn't care what happens to them. 1, 6, 3. Everything is random. Everything will prefer to be disordered. So, this means that over time, things become more chaotic. And energy, like with that paper that I burnt over there, energy will find a way to spread out somewhere. So, like I said, the heat from that found a way to warm up the room a little bit. Why are things sort of ordered at all in the first place? Why can we stand here? Why is I know the ground is all made of the same stuff. Why isn't this like, some part dirt, some part, iron, a little bit of gold flecks on the ground? Why isn't everything always disordered? Well, we can put in our own work to separate stuff. So, again with these dice, we have, let's go like that. Again with the dice, maybe even with cards, it's good to show. You guys ever got a brand new deck of cards? You know that they are ordered in a specific way. I didn't do this. Should have. But imagine you have that fresh deck of cards and you only shuffle it once. And what can you expect to happen? Well, maybe only a few of them got shuffled really well. But the rest, those are all black and there's, a few spades. They're not quite random. I thought the universe liked disorder, though. Well, things have a way of staying in their own little pockets of being ordered, and then we ourselves can put in our own work. I could go and I could put in energy organizing this thing. So now that one goes back here. I'm putting in my own energy to reorganize the universe. So, entropy is a way of measuring how disordered something is, or how much disorder is created. Let me go like this. So, a way to actually measure this is we're talking about thermodynamic processes with entropy. So imagine I light that match, the heat will spread everywhere in this room. And that's increasing the entropy inside of this room. For me to collect all of that heat, if I was able to go out and collect all of the heat that the match gave off, put it back where it was, then I'm decreasing the entropy in the room. I'm making it more organized. But for our thermodynamic entropy, we can do this. Entropy is the variable S. So the change in entropy is defined as QR. And that's just however much energy is being absorbed or given off. Same Q that we've been using before. Over the temperature. And we're going to be using just if I give you an entropy problem, it'll have a constant temperature. If you study more about entropy and about things that are chaotic in nature, You can go into a branch of math called chaos theory, which is pretty interesting. I'll go get that, the triple pendulum again. That's a good representation of something that doesn't behave the same way, even though you expect it to. Let's see. You're talking a bit more about things that are random. And what is randomness? How can you get something more disordered? You can go into statistics, and there's a neat way of actually shuffling cards that makes the deck of cards the most random it can possibly get. So, like you have that deck of cards, it's all in the correct order. If you're at a casino, you don't want that because people can guess which card is where. That's bad for business. They're going to lose a lot of money. Everyone can easily count cards. So, if you want to make your deck of cards as random as possible, you need to shuffle it like this. This is it's called a ripple shuffle. Just a regular shuffle. You do that 7 times. And the deck of cards will be perfectly random. Pass it out, play your game. Shuffle again 7 times. The cards are in no way near the same order they were before. They're completely random. In fact, casinos have their own method of shuffling cards. If you work at a casino and you are the one doing all the cards, each casino has their own method that they train you on. So they might have you do like a method, you like mix them around like this. You might see dealers go like this that can shuffle them up, and then they might have you, okay, now you need to do that ripple shuffle 3 times, and each casino has their own unique way of doing that. So they're different than other casinos. Can't guess what the cards are coming up next. And they have a best chance of you not succeeding at winning the games. Some more stuff on randomness, real quick, because this is the last bit. I have these dice over here. Normal 6-sided dice. We get into statistics and randomness and probability. I say, what's the probability of me rolling a 1 with a 6-sided dice? It's 1 out of 6. I didn't get it. Okay, you do it again. 1 out of 6. Okay, I still didn't get it. If I do 5 of them, nope, didn't get it. Okay, now we can look at what's the probability of me taking these 5 dice, and let's say I roll them out. 4, 4, 6, 6, 2. What's the probability of me getting that again? Well, I can just do the 1 out of 6 to the 5th power. It's a very small number of me getting that value again. These are just 5 dice. Imagine if I did that with 20 dice right here. So what's the probability that this red 3, if that's this blue, that's, I can roll them out, and this is sort of like modeling, like imagine energy is this dice. There's only 5 of them here, but on the microscopic scale, you could think of it as there's millions of these things, and the probability of something always happening the same exact way is going to be very, very low. And that's the idea of entropy, and things will always sort of not go the way you expect. Things will always turn to disorder. When I was 12, I should have told my mom, my room's dirty because the universe tends to be disordered, and what's the point of cleaning it anyway? So we have, I think that is about it for the chapter. So now we'll do a little bit of review on what's going to be on the exam. Yeah.
Can you like explain the picture for the engine? I just had a question on you talked about work being done by the system and on the system. And
Yeah.
if it was done on the system, it was negative, or it was positive, and if it was done by the system, it was negative.
Right.
But isn't that kind of like the opposite in that picture?
So this is for the heat engine. If it goes from hot to cold, you're able to produce positive work. You're able to start moving stuff. Get a nice push to something. This is sort of the reason this is an odd picture, because the Carnot engine, it's then going to use that work and then sort of work backwards in order to complete the cycle. That's why it's not physically possible to have this Carnot engine. I don't know if this...
But so like work being done by the engine, in this case it's positive? Is that?
What do you mean in this case?
Because isn't usually work done by the system negative? Because we have a negative in that equation.
Oh, I see. I see what you're saying. I think that's the way they phrase it. I could just be assuming they say by. I think that's just the way it's providing positive work. How will I say that? Providing, going from hot to cold provides positive work. And don't focus on the by and on. Think about doing this, going from hot to cold provides positive work. And then the Carnot engine sort of goes backwards, and then it goes cold to hot, and it sort of consumes work. Okay. What's going to be on the exam? So stuff from your the last quiz that you had. So that's a good chunk of the exam. So that's all stuff rotational. We were going over torque. We went over angular momentum. We had center of mass. Let me put all this up here. So we had rotational kinematics, or rotational motion, I should say. And then we had those rotational kinematic equations. They're the same exact as those linear ones before. So we had they were the angular velocity, that's this omega, is equal to the initial angular velocity plus the angular acceleration, that's a change in time. We have the angular displacement, that's change of the angle, theta. Plus 1/2 And then we had plus 2 alpha. Change of angular displacement. Okay, so those were a big part of just the general rotational motion chapter. We had the conversion from tangential, from those linear motion to rotational motion. What were they? They were V equals omega times what? R, yep, radius. So the radius of the curvature it's spinning with. We also had same thing for acceleration. So that V and A, those are linear, things moving in a straight line. Then omega is rotational. And alpha is rotational, or angular acceleration times R. Okay.
Can you repeat those last two, please? Sorry.
Right, so we have right here, we have V is linear velocity, and A is linear acceleration. Omega, this fancy W right here, this fancy W, that is angular velocity. This alpha right here is angular acceleration. Sorry? The R is the radius of how the object is spinning, rotating.
Are they the same thing?
Sorry?
The alpha on the first, the pneumatic,
Yeah.
same thing.
Exact same thing. All right. So that's that. What else? We had what did we do after that? We did torque. And that was this fancy lowercase t, that's a tau. It's called tau, equals R cross F. Since we don't want to do a cross product, we're going to do this instead. R F sine theta.
Professor, what's the difference between cross and multiplication?
A cross product is providing you a whole different direction that the thing is pointed. So if I have something, a vector going this way, and I have I have a vector pointed that way, and I have a vector pointed that way, and I say vector R cross F, I use that right hand rule, R cross F, my new vector is pointing up. So that is what a cross product is. It's providing this additional vector that's perpendicular to both of the two. So it's not direct multiplication, it gives you a different type of direction.
So then wouldn't we need to identify that R and F are vectors?
Technically, yeah. Yeah, I would. And that means torque is also a vector. All right. For the second line, I can just say R and F because I can usually just take in the direction with the sine theta. All right, so that's torque. What else did we do in this chapter? We did, so other things with torque. There was the conservation of mechanical energy. And that was this thing. It says the sum of all torques equals 0. So for a system that is in a, it'll say something like equilibrium. This thing is balanced. Remember that seesaw question. It's a mechanical equilibrium problem. So that's saying that all of the torque that, let me put up that seesaw problem again. Just a little picture. Remember we had something over here. We had something over here. So all of the torque that makes it go one way, about the pivot point, there's torque that's trying to make this thing turn counterclockwise. CCW for counterclockwise. And there's this thing over here. There's a force. There's a force. There's a thing over here that's trying to make it twist that way. It's clockwise. So everything that's trying to make it twist in a certain direction, you add all of those things together, you get counterclockwise, clockwise equals 0. And that's because of the conservation of mechanical energy. Or I should say, it wouldn't be plus, it would be, since those are vectors, I'll do this, minus. Okay. We did center of mass. Oops, sorry. That was mass 1 times radius 1, mass 2 times radius 2, however many things there were. All right. After that, what did we have? Angular momentum. So we did a force, and now we will go to momentum. Angular momentum. R cross linear momentum. Since we don't want to do cross products, I'm going to write it like this. And I derived this in class. It was I omega. And what is I? Capital I. That's the moment of inertia. That's how the thing is oriented, how the thing is shaped. Maybe it's a really odd shape and it's hard to spin. So that brings in moment of inertia. I equals mass times however that mass is arranged. How far away is that thing? This was me rolling those two steel wheels down that ramp and seeing which one was fastest. So the thing that had the mass with a small radius has a small moment of inertia, it's able to speed up quicker. The wheel that had the mass far out, extended, it had a large radius, r was big. So large moment of inertia, it's hard to spin. Okay, what else? Was there anything else here? I think that was it. This is basically 2 chapters of stuff. So I'd say look back over your quiz, stuff on rotation. Yeah. Was there anything else? I think that's it.
The kinematic one?
Kinematic?
Related.
Rotational kinematic?
Yeah.
I'm just going to say you don't have to worry about that one.
And then, I mean, it's kind of like angular but conservation.
Right, yeah. If I can put it. That was this. So 1/2 I omega squared. Very similar to the regular kinematic equation. Okay.
Is that translational? Like when you get that answer, is that translational speed?
Speed?
Oh, well, there's like translational.
Translational, so that's just linear. That's the
Yeah.
regular kinematic.
Yeah.
Yeah.
What would be good homeworks to go over?
Should be 6.
So I can't say like there was a best homework for this since there were only 2, and I do a homework per chapter. So otherwise I'd be like do problem 5 on the, so that'd be a bit too specific. And I know the answer of the whole homework, each homework, every homework. That's not good either. So I'd say look at the quizzes and imagine what I could ask that's similar to the quiz and might take about the same amount of time. So it's nothing too crazy, nothing, I know some of the homework problems are outrageous, but similar to the quiz. Okay.
Professor?
Yeah.
So will there be like about this? It'll be similar to exam 1 where there'll be a portion of multiple choice and a portion of free response, correct?
Yes. It'll probably be the same exact format as that first one, where half of the points are multiple choice, half of the points are free response. So that just means the multiple choice might hurt if you get them mostly wrong. What else? Yeah, so this is just the rotational stuff. Then we have the stuff from I guess it would just be the whole assignment 10 since I lumped it all together. But that's everything from thermodynamics. So I'll do one more slide of stuff from that. Is everyone good here? All right. Okay, so really there weren't, let's see. what type of actual problems were we doing? We were doing a lot of like specific heats and pressure and volume and stuff like that. So we were looking at, first thing to look at is, specific heats, just in general. And there was also that heat, change of heat equation, change of energy. That was delta Q equals MCAT. Similar to like your lab that you guys did. This is the whole calorimetry type of problem. If you have me in lab, you had a quiz on this today. Yeah, so stuff like this. What else? Specific heat. I don't think we did it that early, actually. I think we started with like the ideal gas problem or ideal gas formula. Ideal gas. That, we did ideal gas. We talked about what a mole is. Talked about constant pressure and like that hydraulic problem. What else? A lot of stuff from this thermodynamics section was a lot of like definitions. So know what like the first first, second law of thermodynamics is. Look at those PV diagrams. What were they? What did they mean? What did they look like? What were some of them? There was ISO. There are 4. Three of them start with ISO. ISO barometric. Or I could say it's baric, isobaric. I'll have to look that up. Hold on. Baric, barometric, isobaric, isovolumetric, that's the one. There's isothermal. There was adiabatic. What do those look like? Take a, refresh on doing these diagrams. Or I think I had at least one that had you like walk around doing a PV diagram problem on the homework.
Professor?
Yeah.
Will you ask us about like liquids, so like buoyant forces?
Right, yeah, that was in here also. No, that was in between. Right. That was a tiny chapter that was in between. We talked about Archimedes' principle. And that was the buoyant force. The buoyant force is equal to the weight of displaced fluid. And then I did a little bit on, that's where I talked a little bit about pressure. I don't think I did too much with that. States of matter, I did right here. Gas, liquid, solids. What else?
Like radiation, and then there's like heat of fusion.
Then I got into phase, right, and then I got into phase changes with phase changes and the energy required to change from one state of matter to another. Mass times LF. That is the latent heat of fusion. And there was LV. That's the latent heat of vaporization. So if I give you anything like this, I will give you the value of the latent heat of whatever, whatever. You don't have to memorize a table of numbers. I don't expect any of you to do that. I may give the equations like they are on the screen. You're expected to maybe know a bit about it. Maybe go from, a problem like this was going from ice into, ice of water into a liquid. Going from one temperature up through a phase change and then into a liquid. That was a problem that we had. What else?
Professor?
Yeah.
Will you just do problems based on water and not like other substances, like let's say copper? So you don't have do we have to know like the phase change diagram of copper, for example?
I'll have it.
Or just water?
I'll have it simple.
Okay.
You won't have to. I'll say it like this goes from here to here. It turns into a liquid to this.
Okay.
So if I do a solid block of copper, it melts at this temperature. It's the same thing, and you should know that like if I give you latent heat and the mass of the copper, that's still just solid to a liquid. It's still fusion. Latent heat of fusion is going from a solid to a liquid, or a liquid to a solid.
Can copper ever turn into a gas?
I'll say yeah, because there is a lower limit on the temperature in the universe. Since there's no upper limit, eventually you could boil metals. You could turn a metal into a liquid. Think of like a hot, yellow, red hot pool of metal. I imagine you keep heating it up. It'll turn into a gas that is made of pure copper.
Interesting.
On the moon of Saturn, I believe, there is so much methane on Titan, the moon, or one of the moons around Saturn. There's so much methane that there is this sort of seasonal change, and the moon is just in the right spot around the planet, Saturn, that methane is everywhere. It's in the air. It's like how we, expect air to be. Then there are clouds up above made of methane, and it rains methane liquid. And then there are lakes of methane on this moon of Titan, on Saturn, or orbiting Saturn.
How do you know that? Because we haven't visited.
How do I? So there are ways of detecting elements. Let's see. Hold on. Let me Google it. No. No, there are ways of detecting elements, spectroscopy, figuring out elements. And we're able to also gauge the temperature. So we know what's there, we know the temperature of it. We could use this, say, well, at this range, it'll be this temperature, so there's clouds. And we also see there will be methane rain, stuff like that.
Okay.
Also, another cool thing is on Titan, it's lower gravity than here on Earth. So when it does rain liquid methane, it comes down in big globs. They've done the calculations, big globs of liquid methane that slowly fall to the surface.
That's cool.
Yeah. All right. What's next? What did we do next?
What was a delta U there?
Engines? Was there anything else hiding in there?
Delta
Let's see.
U.
What?
The delta U.
Delta U, that's the first law of thermodynamics. I'll just say first law. Delta U. Okay. We had the work done by a gas at a constant pressure. And then we got to the engines, and a little bit more on that. I'll go on the next slide. Okay, it's pretty cool. You were able to comprehend, okay, I know the gravity because it's this size and it's made of this, and I know it's methane and it's this temperature because I know that. So then I could put a model of what this place looks like. I've never been there. And they're only just now having like really good pictures of it with the Hubble. No, I think Voyager went past it. Satellite. Okay, next, or one of the last ones was engines, heat engines. Heat engine. So that's the work produced by a heat engine. I said W-E-N-G. What was that? It had like 3 different forms, and you could say any of them.
I think the easiest is the 1 minus.
Yeah, it is. 1 minus the absolute value of the heat in the cold system, or the energy in the cold system, over the absolute value the heat in the hot system. And then today we did entropy. Very small formula. Entropy. So when you're doing an entropy problem, you just think about whatever type of energy it is. It could be internal energy like heat, or it could be something is moving really fast, so you'd put kinetic energy in here. Or if it's something that's falling, it'd be potential energy. So this is just energy absorbed or emitted, I guess. Yeah. I think that's about it. Does anyone have any questions?
I have a question. So,
Yeah.
For the heat engine, are we calculating work or are we calculating efficiency of that engine?
Oh, there was also efficiency. Yeah. Efficiency of an engine was that?
I think it's 1 minus. I think that's the efficiency.
This is the 1 minus, right? I got it wrong. What was the cold?
Q hot minus Q cold, the absolute value.
Oh, I see. Yeah. It was too easy. I see. Okay. Everyone redo this. Hot minus cold. Hot minus absolute value of cold. There you go. So in this case, the efficiency is 1 minus Q cold over Q hot. And so if we wanted a 100% efficient engine, the energy of that cold system has to be 0. That means we need a temperature of 0 Kelvin. That's the coldest anything can possibly get. So that's sort of the reasoning why that is impossible to get 100% efficient engine. Now I think that's it. Everyone checks, make sure I got everything. All right, so okay. You'll get a formula sheet. Make sure you bring your calculator to scan from. Homework is due tomorrow before midnight. Just try to not wait to the very last minute. Yeah, and I got these tutoring sessions. If you want to go to a time outside of it, just let me know. You can email me. And have a great weekend.